Um, you know that feeling when you're just scrolling through your news feed and you see this massive, bold headline about global security or nuclear threats?
Oh, yeah. Usually accompanied by some intense glowing red graphic of a mushroom cloud.
Exactly. A mushroom cloud or some sinister-looking radiation symbol. And if you're anything like most people, your stomach just instantly drops.
It's a very visceral reaction.
It really is. It can be incredibly overwhelming and, honestly, profoundly confusing to try and navigate those kinds of sensationalized headlines. Because you're left sitting there wondering how much of this is an immediate catastrophic reality and how much is just, well, the media collapsing a highly complex topic into something designed just to get a click.
Right, the click factor.
Yeah. So today we're providing you with a tailored shortcut. We're bypassing the anxiety and the information overload to help you become truly, groundedly well-informed on one of the most heavily discussed topics in the news today.
We are stepping completely away from all that noise,
Hmm.
and we're focusing strictly on the actual mechanics and the underlying physics of these materials.
And to do that, we are starting with some brilliant analytical work by an author named Lev Nemotin. We're pulling directly from his channel, Uncompressed Thinking.
Which is such a great name for what he does.
It really is. The mission of this deep dive is to explore Nemotin's exact source material, specifically an article provocatively titled, "How Many Nuclear Bombs Does Iran Have Today?"
Mm.
We're using his analysis to completely separate the actual literal physics and engineering from the media's imagination.
Mm-hmm.
And just to set the tone right out of the gate for you, our goal today is not to take any political sides whatsoever. We're not endorsing any specific geopolitical viewpoint or, jumping into partisan debates. We are simply acting as your guides to impartially report on the scientific and technical realities outlined in Nemotin's text.
Right, because the political landscape, the diplomatic negotiations, international treaties, all of that is completely outside our scope today. We're looking at this purely through the lens of nuclear physics, metallurgy, and high-level engineering.
Just a science.
Exactly. When you strip away the politics and look solely at the science, as Nemotin points out in his piece, a very different, far more nuanced, and frankly, significantly less dramatic picture begins to emerge for the public.
So we have a really clear roadmap for this deep dive. First, we're going to look at the core math behind an enriched uranium stockpile and what those numbers actually mean.
The literal math of it.
Yep. Second, we'll explore the massive, almost incomprehensible engineering gap between having a pile of radioactive material and having a functioning deployable bomb. And finally, we're going to clear up the widespread media confusion surrounding the concept of dirty bombs.
Which might be the single most misunderstood term in modern news.
Oh, without a doubt.
Because public discussion constantly blurs the boundary between physics, engineering, and imagination. The underlying assumption in almost every headline is that simply possessing a stockpile of enriched uranium automatically translates into an arsenal of ready-to-launch nuclear weapons.
Or at the very least, that this material can be easily taped to some dynamite to construct a devastating dirty bomb.
Right. And Nemotin's work systematically dismantles that assumption by forcing us to look at the actual properties of the materials involved.
So let's start with the premise. The simple question that you see splashed across opinion pages and news banners all the time. How many nuclear bombs does Iran have today? It sounds like a question that should have a simple numerical answer, like counting tanks or airplanes.
But a technically grounded answer requires a very specific set of conditions. You cannot just divide the weight of a uranium stockpile by the weight of a bomb core and get a number. It doesn't work that way.
No.
Nemotin lays out 4 simultaneous, and I should stress, highly optimistic assumptions that you have to make just to even begin doing the theoretical math on this question.
Okay, let's unpack this, because this is where the gap between the headlines and the math really starts to show. According to the text, what are those 4 massive leaps of faith we have to make?
First, you have to assume the baseline material exists in a specific quantity and quality. The working assumption Nemotin uses is that there's roughly 440 kilograms of uranium enriched to about 60% U-235.
I should probably clarify that for anyone who hasn't brushed up on their chemistry lately. Natural uranium comes out of the ground mostly as an isotope called U-238, which is relatively stable. U-235 is the much rarer isotope that can actually sustain a nuclear fission reaction.
Right, the spicy stuff.
Exactly, the spicy stuff. So when the news talks about enrichment, they are talking about the incredibly difficult, highly industrial process of filtering out the U-238 to increase the concentration of that U-235.
Right.
60% enrichment is high, yes, but it is not the 90% or higher that is traditionally considered weapons grade.
Which brings us directly to the second assumption. For the sake of this specific calculation, you must assume that this 440 kilogram stockpile cannot be enriched any further. It is mathematically locked at that 60% state.
Meaning they can't just run it through the centrifuges again?
Exactly. They cannot run it through again to get it to that ideal 90% weapons grade threshold.
So they have a sizable pile of material, but it's technically suboptimal for a traditional, highly efficient weapon.
Yes. The third assumption moves us from chemistry into advanced electronics. You have to assume the possession of high-precision electronic detonators.
Because you aren't just lighting a fuse.
Far from it. In a nuclear device, you have to trigger conventional explosives surrounding the core with literal nanosecond precision to squeeze the material symmetrically. If one detonator fires a fraction of a microsecond too late, the entire reaction fails.
And the fourth assumption from the text.
You have to assume the presence of sophisticated nuclear weapon engineering that is capable of perfectly integrating all of these complex systems together. The enriched material, the nanosecond detonators, the conventional explosives, the firing circuits, they all have to work in perfect, simultaneous harmony within a deployable casing.
Okay, so you have this hypothetical scenario where all four of these highly optimistic assumptions are perfectly in place.
Yeah.
You have the 440 kilos of 60% enriched uranium. You have the impossibly precise detonators. You have the advanced engineering integration. With all that perfectly aligned, what does the actual math dictate?
Even under those absolutely ideal, optimistic assumptions, the number of devices that could theoretically be derived from that specific stockpile is remarkably small. We are talking about a maximum of 3 or 4 devices.
3 or 4, max.
Max. And crucially, Neymotin emphasizes that these would be very low-efficiency nuclear devices. Because you are working with 60% enriched material rather than 90%, a much larger mass is required to achieve criticality, and the resulting reaction is far less optimal.
Wow. That immediately reframes the mental image of some vast, endless arsenal ready to be deployed at a moment's notice. The media narrative makes it sound like thousands of warheads are just rolling off an assembly line. But the math, even when we give the scenario every possible benefit of the doubt regarding their engineering capabilities, points to a handful of low-efficiency devices.
This raises an important question, though. We just looked at the scenario where you assume they have mastered the precision detonators and the sophisticated engineering integration. The third and fourth assumptions.
What I found so striking in Neymotin's notes was the thought experiment of removing those engineering assumptions. Like, what if you just have the material, the 440 kilograms of 60% enriched uranium, but you take away the high-precision detonators and that advanced dynamic compression engineering?
Right. What if you just smash the material together using basic explosives?
Exactly.
Well, if you remove those engineering components, the situation doesn't just change slightly. The physics dictate a completely different outcome. For a nuclear device to function properly, it requires what physicists call dynamic compression.
Which...
You are taking a sphere or cylinder of subcritical uranium and crushing it inward with perfectly timed, shaped explosive charges. It is an incredibly delicate, incredibly forceful sequence of physical events.
It's often compared to trying to squeeze a water balloon perfectly symmetrically from all sides so that it compresses into a tiny, dense marble rather than just squirting out through your fingers.
That is a fantastic analogy, yes. Without those precise systems to squeeze the balloon perfectly, the assembly simply cannot produce the kind of explosion people imagine when they hear the terrifying phrase, nuclear bomb.
Just doesn't work.
It doesn't. The material will start to react, generate an immense amount of heat very quickly, and physically blow itself apart before the actual nuclear chain reaction can fully engage.
Here's where it gets really interesting. Because the way Neymotin describes what actually happens without that engineering is so wildly different from the media narrative. The text uses a very specific and highly illustrative phrase. It says the result would be essentially a brief release of energy, more of physical puff than a nuclear detonation.
A physical puff. Without the precise engineering to force and hold the fissile material together for the optimal fraction of a microsecond, it fizzles. The conventional explosives go off, the uranium gets hot, it expands, and the expansion pushes the uranium atoms too far apart to sustain the reaction. It is a self-terminating event.
I was reading the analogy Neymotin uses to quantify that puff, and it completely changes the scale of the threat. He writes that in practical terms, the energy released from this poorly engineered assembly would only be comparable to powering several incandescent light bulbs for a short moment.
Light bulbs.
Yeah. The public hears the words enriched uranium and immediately pictures a devastated metropolis with a miles-high mushroom cloud.
But the physics tells us that without the correct, highly sophisticated integration systems, you get enough energy to light up a few bulbs in your living room for a fraction of a second, accompanied by a conventional, localized explosion.
It sounds more like a very expensive, very dangerous science fair volcano that just sort of burps, rather than an action movie doomsday
It
device.
really does.
It may not make for sensational television graphics, but as the author notes, it is much closer to the underlying physics.
Let me pause for a second. What stands out to you here? Think about how often you see news segments using glowing, apocalyptic animations the moment the word uranium is mentioned.
All the time.
Understanding this specific distinction, the massive chasm between a pile of reactive material and a dynamically compressed, precision-engineered device, should fundamentally alter how you interpret those sensational graphics.
Because they're skipping a few steps.
Huge steps. The media is showing you the result of assumed perfected engineering. They are not showing you the reality of the raw material itself.
If the listener actually understands the science, the media literacy naturally follows. It takes the panic out of the equation and replaces it with an understanding of mechanics.
Exact.
But of course, the media narrative doesn't stop at just nuclear detonations. If an analyst goes on television and admits that building a proper dynamic compression bomb is an incredibly high hurdle, the anchor will almost immediately pivot to the next terrifying buzzword.
Oh, yes, the dirty bomb. This is the next major misconception Namotin tackles in the text, and it is perhaps the most pervasive myth in modern security reporting.
The idea presented to the public is usually something along the lines of, well, if they can't build a complex implosion weapon, they can just take that stockpile of 60% enriched uranium, strap it to some dynamite, put it in a truck, and they have a dirty bomb that will render a major city completely uninhabitable for centuries.
What's fascinating here is how entirely misunderstood the concept of a dirty bomb actually is, starting with its basic definition.
Let's hear it.
A dirty bomb is not a nuclear weapon. It does not utilize a nuclear chain reaction or the splitting of atoms to generate a massive explosive yield. It is simply a conventional explosive, like TNT or C4, that is used to scatter highly radioactive material into the surrounding environment. The explosion itself is just normal fire and concussive force.
I was looking at Namotin's breakdown, and it raised a really interesting contradiction. Because if the goal is just to scatter radioactive material using conventional explosives, you would intuitively think that 60% enriched uranium would fit the bill perfectly.
It seems logical at first glance.
Right, it's radioactive material. It seems like it would be the exact right ingredient for a radiological terror scenario.
But chemically and physically, it is completely the wrong material for that specific job. The effectiveness of a radiological dispersal device, a dirty bomb, depends entirely on the specific isotopic properties of the radioactive material you are putting inside it.
It's not one size fits all.
Not at all. To be an effective area denial weapon, the material needs to possess high radioactivity, strong gamma radiation emissions, a relatively long half-life, and the physical ability to cause persistent, dangerous environmental contamination.
And here's where it gets crazy to me. Highly enriched uranium simply doesn't check those boxes, which feels completely counterintuitive to everything we see in movies.
It really is counterintuitive.
When experts discuss actual, credible, dirty bomb scenarios, they aren't looking at uranium. They are looking at entirely different materials, usually isotopes found in spent nuclear fuel or medical radiation sources like cobalt-60 or industrial sources like cesium-137.
Because those specific materials, cobalt-60 and cesium-137, are intensely radioactive. They emit powerful gamma rays, which are highly penetrating forms of radiation. If dispersed over an area, they remain incredibly hazardous to human health for extended periods, making cleanup an absolute nightmare.
And uranium doesn't do that.
Highly enriched uranium, despite its massive strategic importance as a potential fuel for a chain reaction, does not share these radiological characteristics.
What surprised me most in Namotin's notes was learning just how weak the ambient radiation of uranium metal actually is compared to those medical or industrial isotopes.
Namotin points out several physical facts to ground this discussion. First, uranium emits relatively weak radiation overall compared to common radiological sources. But more importantly, the type of radiation it primarily emits is completely unsuited for a dirty bomb. Much of the radiation emitted by uranium consists of alpha particles.
And for a quick physics refresher for you listening, an alpha particle is relatively heavy and slow-moving on a subatomic scale. If gamma radiation is like a high-speed bullet that can pass through walls and bodies, an alpha particle is more like a thrown ping pong ball.
A ping pong ball is a good way to picture it.
It can be easily stopped by something as simple as a few inches of air, a piece of paper, or even the outer dead layer of your skin. It does not penetrate like the strong gamma radiation required to sicken a population from a distance.
Exactly. And because of its modest environmental radiological impact, if you took highly enriched uranium metal and dispersed it with a conventional explosion, the primary result would simply be the scattering of heavy metal dust.
Just dust.
Dust. It would be an environmental hazard, certainly. Breathing in heavy metal dust of any kind is bad for your lungs and kidneys. It would be very much like an explosion at a lead processing factory.
A localized toxic cleanup site, but absolutely not the kind of persistent, highly dangerous radiological contamination associated with the public's fear of a dirty bomb. You wouldn't have to abandon the city for thousands of years.
Enriched uranium is strategically important if you are capable of performing complex nuclear engineering to force a fission chain reaction. But it is exceptionally poorly suited for a radiological peril scenario. Even if you constructed a dispersal device out of this specific uranium material, detonating it wouldn't yield the catastrophic, glowing wasteland effect the media loves to speculate about.
It is so refreshing to hear this broken down by the actual measurable properties of the materials. The news tends to lump everything that is even vaguely related to nuclear science, whether it's uranium, plutonium, spent fuel, medical isotopes, all into one terrifying glowing green category.
If we connect this to the bigger picture, the core thesis of uncompressed thinking really shines through here. The difference between nuclear physics and public narratives is often striking. Possessing enriched uranium does not automatically produce a nuclear weapon due to the immense engineering hurdles, and it does not automatically provide material suitable for a dirty bomb due to its specific radiological properties.
Those distinctions matter so much because they govern how nations actually respond to these developments in the real world.
Because without those distinctions, complex technological realities simply collapse. They collapse into a single dramatic headline designed to capture attention. And once that collapse happens, the public conversation completely shifts away from physical reality, away from the math and the metallurgy, and purely into wild speculation and fear.
So what does this all mean? For you, the listener, navigating the daily flood of news, the final crucial takeaway from Neymotin's analysis is the absolute necessity of differentiating between three distinct things. You have to separate fissile materials, engineered nuclear devices, and radioactive contamination sources.
They are not synonyms.
Not at all. They represent entirely different branches of science and completely different levels of threat.
Highly enriched uranium is a strategically significant material because, under the right, highly specific engineering conditions, it can serve as fuel. But material alone does not equal a weapon, and uranium itself is not a highly effective radiological dispersal material. A sober, rational discussion of global security risks must keep these categories distinct.
Because if you blur those lines, nuclear physics disappears entirely behind the headlines.
It does.
And as Neymotin concludes, the distance between the media's imagination and the actual literal physics isn't just a matter of slight exaggeration. It is measured in orders of magnitude. It is the literal difference between a city-leveling event and a physical puff that barely powers a few living room light bulbs for a fraction of a second.
The raw ingredients are only a fraction of the story. The true barrier is, and always has been, the engineering.
Before we wrap up this deep dive, we want to leave you with a thought to mull over on your own, something that builds on Neymotin's concept of uncompressed thinking but stretches beyond just nuclear physics. If the media consistently collapses the highly complex multi-step engineering of nuclear weapons into simple scare headlines just because a country possesses the raw material, what other highly technical global threats, like artificial intelligence or bioengineering, are we completely misunderstanding today because we are confusing the raw ingredients with the finished engineered product? Think about that next time you scroll past a terrifying headline. Thanks for taking this deep dive with us.